Hello. Please hit like button and subscribe my channel. Also press bell icon for future video notifications. Thanks.
Since element 99, Einsteinium, was discovered in 1952 at the Department of Energy's Lawrence Berkeley National Laboratory Berkeley Lab from the debris of the first hydrogen bomb, scientists have performed very few experiments with it because it is so hard to create and is exceptionally radioactive. Published in the journal Nature, the study, Structural and Spectroscopic Characterization of an Einsteinium Complex, was co-led by Berkeley Lab scientist Rebecca Abergel and Los Alamos National Laboratory scientist Stosh Kozimor, and included scientists from the two laboratories, UC Berkeley, and with less than 250 nanograms of the element, the team measured the first-ever Einsteinium bond distance, a basic property of an element's interactions with other atoms and molecules. "There's not much known about Einsteinium," said Abergel, who leads Berkeley Lab's heavy element chemistry groupon as an assistant professor in UC Berkeley's nuclear engineering department. "It's a remarkable achievement that we were able to work with this small amount of material and do inorganic chemistry." It's significant because the more we understand about its chemical behavior, the more we can apply this understanding for the development of new materials or new technologies, not necessarily just with Einsteinium, but with the rest of the actinides too. And we can establish trends in the periodic table. Short-lived and hard-to-make, Abergel and her team used experimental facilities not available decades ago when Einsteinium was first discovered, the Molecular Foundry at Berkeley Lab and the Stanford Synchrotron Radiation Light Source (SSRL) at SLAC. But first, getting the sample in a usable form was almost half the battle. "This whole paper is a long series of unfortunate events," she said wryly. The material was made at Oak Ridge National Laboratory's high-flux isotope reactor, one of only a few places in the world that is capable of making Einsteinium, which involves bombarding curium targets with neutrons to trigger a long chain of nuclear reactions. The first problem they encountered was that the sample was contaminated with a significant amount of californium, as making pure Einsteinium in a usable quantity is extraordinarily challenging. So they had to scrap their original plan to use X-ray crystallography, which is considered the gold standard for obtaining structural information on highly radioactive molecules but requires a pure sample of metal, and instead came up with a new way to make samples and leverage element specify. Researchers at Los Alamos provided critical assistance in this step by designing a sample holder uniquely suited to the challenges intrinsic to Einsteinium. Then, contending with radioactive decay was another challenge. The Berkeley Lab team conducted their experiments with Einsteinium-254, one of the more stable isotopes of the element. It has a half-life of 276 days, which is the time for half of the material to decay. Although the team was able to conduct many of the experiments before the coronavirus pandemic, they had plans for follow-up experiments that got interrupted thanks to pandemic-related shutdowns. By the time they were able to get back into their lab last summer, most of the sample was gone. Bond distance and beyond still, the researchers were able to measure a bond distance with Einsteinium and also discovered some physical chemistry behavior that was different from what would be expected from the actinide series, which are the elements on the bottom row of the periodic table. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.